Hello everyone, I'm Young First. Welcome to my channel. This is a series about a self-mock technical interview in English. Today in this episode, we will to solve the daily problem of LeetCode. So let's start. Today the difficulty is a medium. So I think we should resolve this problem within 20 minutes in an interview. So let's start. Unique binary search trees. Given an integer n, return the numbers of structurally unique binary search trees, which has exactly n nodes of unique values from 1 to n. So it's not very clearly. So let's look at the example. Say this is 3. So we have four binary search tree, which the node is from 1 to n. Yes. So it's more clear when we look at the example. We have an integer n, and we need to get the number of the unique binary trees, which has exactly n nodes. For example, 3 is 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Those 5 binary search tree are valid binary search tree, and it has 3 nodes, and there is no other binary trees that has nodes. So we need to return 5, and the n in fact is very small, which is from 1 to 19. So what do you think? Um, I there I think look at about some sample. For example, if n is 0, no, there is no 0. If it's 1, so there is just one binary search tree. It's just one node. And if there is 2, n equals 2, I think there is let's do that. There is first 1, and then this is 2, and this is 2, and this is 1. There is two binary search tree, and when n is 3, how do we construct the binary search tree? And like two, we first try to put every node as the root node, and we put the remain nodes in the left or in the right. So for n equal to 3, we first put 1, and then we put put 2, and finally we put 3 as the root node, and then for 1 is the root. We have 2 and 3, so we can recursively call the num trace the same function with argument equal to 2, and and 2 with n equals 2, there this is 2, so there is 2 situations when one is the root tree, and if 2 is the root node, we have 1 and 3 here, so we need to call numTrace function with argument 1 and with argument 1, and we need to multiply the two numbers because they are independently they are independent with each other. With the 3 is the root node, it's very similar with the 1 is the root node. We have 2 nodes in the left, so we recursively call the same trace in the left, and we there is no node in the right, so it's 1. So finally we get our answer. It's recursively solution. We need to iterate every possible root node, and after we choose the root node, it divided the whole nodes into 2 parts, left part and right part, and we recursively call the function, and we multiply the two answer. So let's do that, and hope maybe we can analyze the time complexity first, because we need to iterate our possible root, so it's n. Then we need to call the two functions, to the left tree and the left tree. So it's difficult to analyze it. In fact, the answer, the time complexity is the answer. In fact, if the answer is 5, we that 5, and so how do we present the time complexity with the n? I'm not sure. Okay. And the space complexity is the same as the time complexity, because we need to call the last function with argument 1. To be honest, I'm I'm not sure about the time complexity and space complexity, but I believe that my solution can pass. So let's do our function. Let's do our implementation. So here is n. N is n inter and return inter. If n is 0, the type is 1. And if n is 1, it's still 1, 2. If it's larger than 1, we need to iterate every possible node, and here is the answer, and we need to sum the left and multiply the right. I. Here is I. We put 1 here, left is 0, and here. And we need to return ons because there is some duplicate computation. So we need a catch here. So with this annotation, we can catch the answer which we have calculated. So we can avoid the duplicate calculation. So we need to return the n here. So let's run our code. The code is very short and very clearly. Let's try to submit that. Yes, we success. The solution is right. I did this before 1 year ago and 2 years ago. Now I want to see some discussion and find out the time complexity. Let's do some. Let's find the most root. Okay. There is no time complexity analyze tool. I think maybe it's very difficult to analyze that. Okay. Oh, so it's a Catlin number. If you are not good at the mathematics, it's impossible to analyze the time complexity. So, okay, I think the time complexity is a combination number, which we call the Catlin number. Yeah, it's good. It's good to know the Catlin number and the time complexity, but I think it's fine if you don't know it in a interview because it's a super difficult and mathematically solution. So I think you just need to learn how to solve this problem of with the recursive and the dynamic programming. So I think this is my today's video. Thank you for your watching. Bye bye. See you tomorrow.